presentation on high-resolution scintillation materials and detectors. I'm happy to be present here together with Cody. I'm Paul Schotanus at Scionix, and I'd like to share with you the state-of-the-art of current commercially available high-resolution scintillation materials and detectors. What can they offer you, and what you should keep in mind when designing sensors around these instruments. Let's go to the presentation. Scintillation detectors are standard tools in many disciplines. Here is a list on this overview, as by far not extensive. The applications range from medical, security, high energy, nuclear physics, geology, and many more. And we should keep in mind that the requirements in all these applications are totally different. The energies can range from a few keV to very many hundreds of MeV in high energy physics. The temperatures can range from room temperature, most frequently, to very cold in the Arctic, up to very high temperatures in geological exploration. And each discipline has its own key performance indicators, which means that the definition of a better detector depends very much on the actual application. The history of scintillation detectors is closely linked to the development of light detectors. We see here a graph, I think, made by Delft University some years ago, where you see the gradual growth of new scintillators over the years. Photomultipliers were developed actually in the 1940s, and there the flow of new scintillators started. Started with good old sodium iodide, still a very frequently used material these days. Around 2000, there were new materials developed, lanthanum chloride and lanthanum bromide. Those materials we'll call now high-resolution materials or high-resolution crystals. And the reason why they are called like this is we can achieve very good energy resolutions with those materials. They were followed later by other materials like cerium bromide, CLYC, strontium iodide, CLYC, GAGG, and many more. In the beginning, especially after 9/11, oops, I'm back, Cody.
Sorry.
In the beginning, especially after 9/11, the focus was very strongly on the energy resolution at 662 KeV Gamma rays, pushed by security needs. And this whole development has led to the development of these very interesting materials. Proportionality means that the light output as a function of the energy per unit energy is constant. A proportional crystal, this value is close to unity. On the existing alkali halides, we see this number rises up to 1.4, going from 1 MeV to a few tens of keV. Whereas on proportional crystals, lanthanum bromide or cerium bromide, this number is much more constant. And because we have proportional crystals, we can achieve a very good energy resolution, close to 3 and 4%. So what is high resolution? We usually mean energy resolution. High purity germanium detectors are direct interaction devices, so there's no light produced when radiation passes through the material. We have direct electron hole pair production. There the resolution is roughly 2 keV over the entire energy range from a few keV to MeV. And this gives you a really superb energy spectrum. In the middle of this slide, you see the spectrum of a regular germanium detector. If you convert that resolution in percent for different energies, 60 keV to cobalt 60, 1.3 MeV, we see numbers of resolution going from 3% to 0.15%. Now, when the table below there, you see the best numbers that you can achieve with scintillation materials. There you see the numbers are quite a lot higher, especially in the 1 MeV region, where you see that the high purity germanium detector really has an order of magnitude better energy resolution. With energy resolution, we mean the width of the total absorption photoelectric peak, like you see in the spectrum to the right. So the real high resolution detector is actually a germanium detector. But germanium is a quite low Z density. You need to cool them, the size, and those are significant disadvantages. This means that with scintillation detectors, we can offer very adequately do our detection job. So what's a good energy resolution good for? Well, two answers there. Most important, to detect gamma lines that are close together, or gamma lines that are superimposed on a very large background. You see, for example, here two spectra. One spectrum to the left is an LBC crystal, and to the right is a spectrum of a good sodium iodide detector, and the source is barium-133, with the line in the middle 356 keV. The difference is quite striking. You see a lot of structure in the peaks around the 300 keV maximum, whereas with a sodium iodide detector you can hardly discriminate it. So it's clear that a good energy resolution is important for spectroscopy. When you're measuring a known source for a pipe, for industrial applications, it doesn't make any sense to use a high resolution material or detector. You don't need it. An example where you want to deconvolve, separate peaks that are very closely together is, for example, radioisotope identifiers. To the right you see an example of those devices. But we should realize that resolution is not always the most important parameter. Other parameters play a very important role as well in the quality of these instruments. For example, when the resolution of a scintillation detector approaches the 3 or 4%, stability of the spectrum becomes extremely important. We should realize that scintillation detectors show a temperature-dependent gain. To stabilize scintillation detectors is far from trivial. It is possible, we have to take special provisions. And in reality, the difference in performance, identification power, between 3 and 4% detectors is marginal, also because of this stability issue. The other application where a good resolution is very important is when we want to see small gamma ray lines superimposed on a big background. You see, for example, here a spectrum from a prompt neutron gamma analysis application. Do realize that the spectrum here is logarithmic. You see some small blips there, and of course it's clear that when the resolution is better, you have a more narrow peak, and they will more quickly come out of this background. You'll be able to measure the content of those peaks. These energies are quite high here, 5 MeV you see there on the scale. You shouldn't forget that at multi-MeV energies, the homogeneity response along the crystal's length also plays a very important role. You can calculate then that if you have an inhomogeneity of a few percent, this adds to the basic resolution of the detector. It's a fact that many high-resolution materials have a fast decay because it turns out that often they are cerium doped, like for example lanthanum bromide or cerium bromide, which is a pure scintillator, LBC and GAGG. And those cerium doping means that the decay times of the scintillators are of the order of tens of nanoseconds. Strontium iodide is actually an exception. We'll come to that later. But fast decay times mean you can do fast timing. And if there's only a fast component, you can run the detector at very high count rates of the order of a megahertz. To the graph to the right, you see the rise time of different materials, cerium bromide and lanthanum bromide. You see there that cerium bromide is extremely fast rise time. This allows you to use cerium bromide for fast timing applications. The basic limitation of the resolution of scintillation materials is determined by an equation. And this equation you see here at the right of this slide. The equation contains three terms. First of all, we have the intrinsic proportionality. Second, we have the statistics. And then there are inhomogeneity effects and full multiplier tube effects. In the middle curve, you see the line, and this is the theoretical line based on statistics. And you see that all the existing scintillators are above that line, so they have a worse resolution than actually you could expect. And this is caused by the non-proportionality. But it means also that new materials implies new challenges. Because the ideal energy resolution that you read in literature is only achieved under the ideal circumstances, when the maximum number of photoelectrons is measured and the optimum homogeneity is actually achieved. And this means that you have to select the quantum efficiency of your light detector or full multiplier tube with a special high quantum efficiency cathode. And you have to choose the light detector surface for a multiplier tube or a silicon detector the same size or larger than the scintillator. And of course, you have to use a suitable size glass or quartz window, because it happens to be that many of these nice high-resolution crystals are quite hygroscopic. So it means that you have to use really an ideal configuration for the light detection in order to achieve the best energy resolution and get a real high-resolution detector using a high-resolution crystal. Some configurations, for example, are not possible with a high-resolution crystal and still achieve a good resolution in the detector. Like you see to the left here, this is a crystal with a hole in it with 4 light detection points. In this case, photomultipliers. It could also be a silicon detector. And to the right, you see a scintillator that has a size larger than the photomultiplier. In this case, the ideal good energy resolution, 3 or 4%, you cannot really achieve. So the use of high-resolution crystals in an instrument, in a detector, does not always lead to a high-resolution detector. All the other parameters need to be optimized. And that is something that many people don't realize when they want to design new sensors using these fascinating crystals. Another thing is the low energy behavior. It happens to be that most high-resolution crystals, the lanthanum bromide, cerium bromide, and so on, the light output decreases at lower energies. So it means that at a low energy of, for example, 6 keV for X-rays, the best resolution is not achieved with a high-resolution crystal, but actually is achieved by classic sodium iodide crystals. You see here some spectra at 6 keV, where we can achieve a resolution of roughly 30% for sodium iodide and about 40% for cerium bromide. An interesting thing also I'd like to mention is that the energy resolution of novel high-resolution crystals as published in the literature is always reported with high quantum efficiency photomultipliers, and is then compared to data of classic crystals where standard photomultiplier tubes are used. It is not a real fair comparison. But we compare different instruments. We have a new instrument with a novel sensor, a novel photomultiplier, and a classic sensor. But if we would use high quantum efficiency photomultipliers also on standard crystals, we would obtain rather different numbers. And this table I show you here to the bottom of this slide here shows you some resolution for some classic materials, sodium iodide, cesium iodide, and BGO, and some high resolution materials, cerium bromide, lanthanum bromide, and LBC, and at different energies, 60 keV, 662 keV, and 2600 keV. And there you see that when you use a high resolution photomultiplier, a good quantum efficiency photomultiplier, you can achieve with sodium iodide resolutions below 6%. And at 60 keV, the resolution for example for americium, 59.5 keV, becomes in the region of 7 to 8%. In the middle, at the bottom, you see the spectrum from a sodium iodide crystal, a regular crystal, read out with a high quantum efficiency photomultiplier. There you see a lot of structure in the lines in the beginning of the spectrum and this good resolution of 7%. This is something that not many people realize. The spectrum to the left actually is the 5.6% at 662 keV.
Continue.
Okay, then I would like to go to the section of where we are with the application of new materials. Lanthanum bromide, been around for 20 years now, is a mature material used on quite an extensive scale. The disadvantage of this material is the lanthanum-138 background, which is characterized by a beta emission and several gamma lines. In addition, there is an alpha contamination that we are having actually in most rare earth scintillators. You see that's the right part of the spectrum. Cerium bromide, that was developed sometime later, doesn't have this contamination of lanthanum-138, and this means that the spectrum is quite pure, and this is shown in the spectrum to the right here, where you see only some emissions of 511 keV, which is cosmics. You see a little potassium-40 from the photomultiplier tube, and there is some little lines from the aluminum, some radium. The interesting thing about cerium bromide is the Cody.
There we go.
The absence of slow components in the spectrum, and this means you can really run a detector at megahertz count rate, for example, plasma physics experiments. Interesting also to note is that at high energies, let's say 5 to 10 MeV, the resolution of cerium bromide becomes almost the same as lanthanum bromide. The light output of cerium bromide is a little less than lanthanum bromide, but at higher energies, this actually has no impact on the resolution. So cerium bromide has no beta background, an extremely small alpha background, which we've been able to reduce to less than 0.01 count per second per cc. You see a spectrum there of CZ137 shows you this resolution, which is less than 4%. Cerium bromide is used in space applications because of its very low background and good energy resolution. Plasma physics, as I said, for the speed and the radiation hardness, and also in positron annihilation lifetime spectroscopy because of the time resolution and the simultaneous good energy resolution. It's used more and more in environmental applications because of the low background and the good resolution, and in nuclear physics. The nice thing about cerium bromide is that it is an intrinsic scintillator. It has a homogeneous response and a decay time, roughly 17 to 25 nanoseconds, depending a little on the size. There's no slow components. It's radiation hard particles, neutrons, and the emission wavelength is a little higher than lanthanum bromide. At the moment, cerium bromide is available up to 100 millimeter diameter, 127 millimeter long. The next material I'd like to show you is LBC, lanthanum bromochloride, which actually is a mixed crystal between lanthanum bromide and lanthanum chloride. It has similar properties, same light output as the well-known lanthanum bromide. Typical resolutions are 3% at 662 keV and has a fast component decay of roughly 35 nanoseconds. LBC suffers actually from the same background due to lanthanum 138 as lanthanum bromide. Some spectra I'll show here below. One is a cesium spectrum, the other one is a spectrum of cobalt 57, 122, and you can see the separation between 122 and 136 keV. Another little newer high-resolution material is strontium iodide. It's an extremely bright scintillator. It is proportional. It means that we can achieve good resolution with it. It suffers from a rather small Stokes shift. This means that there is some self-absorption in the material, and this means that when the crystal size increases, resolution degrades a little. Regardless of this, it's still possible to achieve resolution between 3 and 3.5% full width Fmax at 662 keV, and a good resolution at 122 keV. The light yield is very high, and this means that at low energies, we can also achieve very good resolutions. It's radiopure, no contaminants, and this crystal actually may find interesting applications in low background, high resolution spectroscopy. The material is slow, it has a many microsecond decay time, which means it's a little more difficult to use it at a higher count rate, but this very brightness in the low energy range may open up some very interesting new applications, I think. CLYC, cesium, lithium, yttrium chloride, also cerium dope material. It has a little less density than cerium bromide. Light output is significantly less than cerium bromide, but it contains lithium. And with lithium, it means we can detect neutrons with it because of an interaction between the thermal neutrons and the lithium, nuclear reaction. The neutron peak will appear at roughly 3.1 to 3.3 MeV. It's very sharp. We can even do fast neutron spectroscopy using the chlorine-35 interaction. The material doesn't contain that much lithium, which means we need about 12.7 millimeter for 90% thermal neutron absorption, and this is for 95% enriched lithium-6. As I said, the light output is a little low, which means the resolution is not 3%, but more 4 to 5%. It has some slow components, which gives some problems in high count rate application, but still a very interesting material. And by using pulse rate analysis and pulse shape discrimination, we can very nicely separate thermal neutrons from gammas. We show a scatter plot to the right here, and this blob there to the right, that's the thermal neutron peak. These days, digital electronics is really replacing everything that's like NIN applications. And this digital electronics that we can buy these days, it makes it very easy to do these kind of scatter plots. The last material I'd like to discuss is GAGG. It's an oxide crystal. It has quite a high density. It has an emission at 520 nanometer, so in the yellow. You can see this, the material looks yellow. It's quite bright, 50,000 photons per MeV. It's proportional. Actually, it's the first not hygroscopic high light output material that is proportional. It's a high melting point, about almost 2000 degrees centigrade, which means it has an impact on the cost. It's not that frequently used yet in instruments, but since we can cut very efficient pixels out of it, it may find some interesting applications with silicon photomultipliers and matrix elements, for example. Also, the resolution is not as good as you can achieve with cerium bromide, for example, with CLYC, because the emission is in the yellow, and the light detectors we have at the moment are not really optimized for a yellow sensitivity. No new generation scintillator will be ideal material are there to state. There will be some disadvantages. Most of the materials we discussed today are hygroscopic, which is a disadvantage, but this can be overcome by proper encapsulation. The bottom line in application of material is often the cost, and this relates strongly to the growing yield, which means how many chemicals you need to grow a material that you can cut into a size you can use in an instrument. The material cost is seldom a real issue there. One of the reasons that cerium bromide and lanthanum bromide or LBC are relatively expensive is to have an alinear expansion coefficient. This makes it difficult to grow these materials to have a very good yield in growth. At the moment, tuning the proportionality, the property I discussed in the beginning of this talk, is a real hot topic. We're trying to add things to scintillators by making them more proportional and to push down the resolution more with LBC or lanthanum bromide to 2.5% and cerium bromide close to 3%. We should not forget that energy resolution is not all that counts. We should look at the different performances that are important for a specific application. And we shouldn't forget that all new high-resolution scintillators will exceed in cost an order of magnitude at least compared to classic materials, say alkali halides. This brings me to the summary of this presentation. Very good resolution scintillators, 3 to 4%, are very useful in very many applications when you want to do spectroscopy or want to see peaks on a big background, but they're not always needed. Special provisions in design and readout need to be taken in order to achieve a good energy resolution out of your scintillation detector. Just using a good high-resolution crystal is not enough. And the interesting thing is that also classic crystals will benefit from this approach. Proportional crystals, high-resolution crystals, do not always outperform classic scintillators. It depends very much of your application. When the resolution goes to 3–4%, the stability of your system is very important for a high-resolution detector. Then we see that the number of available novel scintillators, proportional scintillators, is increasing every day. Many materials are presented. Most of them will not make it to commercial availability. But we have still at the moment quite a lot of crystals available, and this makes the users very difficult. But we at Scionix, we're there to help you, to assist you to choose the best scintillator for your application. Contact us via our website, I would say. Send us an email to BNC or to us directly. Thank you.
All right. Thank you very much, Paul. That goes ahead and squares away the presentation segment of this webinar. What we will be doing now is moving on to questions. We've had some roll in as the presentation was occurring, so I will be going in order of the questions I see in the chat room. Paul, the first question is for slide 14. There is a webinar viewer who is curious about the data acquisition system for these charts, if you happen to know that.
These spectra were measured using a classic analog acquisition system So a classic NIMBIN spectroscopic amplifier with a shaping time of 12 microseconds, classic preamplifier. But you can as well use a detector with 14 pins, couple it to a digital base, and set the digital shaping parameters to the same values to get the same result.
Okay, and would that happen to lend information to why the cobalt 57 peak channel seems to be very close to the CS137 peak?
No, the calibration is different. Those spectrum don't have the same calibration. It's not a calibration in KeVs. It's an arbitrary channel. The two peaks in the spectrum at the bottom is 122 and 136.
Okay, excellent. Next question I have here is from Eric, and he's curious about how all these materials you mentioned relate to each other in terms of radio purity.
Cerium bromide actually is the most radio pure high resolution material, but it's not as radio pure as strontium iodide. The most radio pure material actually is strontium iodide. Unfortunately, we cannot use it in really large dimensions. Lanthanum bromide, LBC are not radio pure at all. CLYC is also relatively radio pure, but it is a rare earth cerium emission. So I'm not totally sure about that.
All right, thank you. And I have another Eric here asking a slightly different question. I believe this was answered in chat, but are there any crystal size limitations of any of these materials compared to sodium iodide, for example?
That's a very good question. The nice thing is about sodium iodide, our good old classic material, you can grow it in 400 millimeter diameter and about 400 millimeter high. And this is absolutely not possible with high resolution materials, whether you speak about LBC, cerium bromide, or CLYC or whatever. The limitation with the materials lanthanum bromide or cerium bromide stops at about, at the moment we are about 100 millimeter, 4-inch, 5-inch maybe. And as big as you grow sodium iodide or cesium iodide, you'll never be able to make those kind of crystals, again, because of the non-isotropic expansion coefficient that I earlier mentioned. The price would actually be out of the roof.
All right. Excellent. And I have a question from Alexi here, and they are wondering about lateral resolution. They're asking, what's the highest possible resolution you can achieve in a detector? Is there
the best possible resolution? I don't understand.
Alexi, if possible, may you provide a bit more context to your question, and then we'd be happy to answer it. I'll take a note of that, but move on to the next question, which comes from Alexander, who is curious if you are capable of comparing the natural BKG spectra in BKG measured by lanthanum bromide. Let me go ahead and read this one out in full because it has a bit of specific info. They want to compare the natural BKG spectra with TI-208 K40 dominated peaks and BKG measured by lanthanum bromide.
Well, the lanthanum bromide spectrum, of course, has an intrinsic background due to the lanthanum 138 presence, which is the same in LBC. But if he sends us an email, we can send him some spectra of the background we measured with cerium bromide or with the lanthanum compounds. It's also in some of our data sheets. I suggest to send an email and we can reply that.
All right. Yep. Definitely get in contact with Scionix Alexander, and we are more than happy to follow up directly. And looks like that's it just for a moment. There are several people typing. All right. I have another question. This question is actually suggesting, are you capable of commenting on the improvement of light extraction from scintillators to utilize the full potential of the photon statistics?
Yeah, it's very important that a scintillator surface receives the proper surface treatment to get the maximum amount of photons out of the crystal. And this surface treatment depends on the size. If you have a long, thin crystal, or you have a crystal that is about the same diameter as height. And I think that at Scionix, we know how to do that. And I think that we're getting the optimum amount of photons out of the material using our technologies. I wouldn't know any other way how to improve that.
Excellent. So all contact information that is on this current slide will directly reach either Paul or BNC.
I saw an interesting question from Machi Kapusta. He asked if nanoscintillators are possible. That's a good question. I think that nanoscintillators is a very interesting concept, but we still have to see the birth certificate of a nanoscintillator in the form of a pulse height spectrum. When we see that, then we know it's possible.
Great. And then Alexei just sent in another message with more context on that lateral resolution question. They, if you can read it, they have an ion beam that can focus up to 10 nanometers in size. They want to shine it on the scintillator that is placed on top of the detector with pixel pitch, let's say 10 micrometers. Would there be a scintillator that has the same or a similar lateral resolution? And their general question is, what are the two closest spots in space one can resolve with the use of a scintillator?
It depends very much on the light spread, but I would like to have this question in an email. Then I can sit down in front of it, think about it, and reply to it, because it's a little complicated.
All right, definitely. Looks like we're emptied out on questions again, but we'll go ahead and take a couple more, and then we'll probably start moving the conversations to direct contact. Just again, I want to thank everybody for attending. Apologies for those who had audio issues to start, but there will be a full playback available of this presentation that you can review at your leisure. That will be sent over or provided upon request.
Thanks for listening.
All right. Just have a... Oh, looks like there's several people typing. And then once we conclude on that batch, we'll move on to the wrap-up. All right, I have a question from Li Quan, who is asking, which scintillator has the least after pulse after a bright shining?
Cerium bromide.
Cerium
I
bromide?
have data on that also.
Great.
Anyway, of the high resolution materials. That's what we're discussing here today.
Okay. And then I don't think I see any more questions. We have one more person typing, two more actually. All right, so Alexander again is asking, so he says that the timing resolution of the scintillator is important in targeted neutron techniques. What about the time of grown-up pulses in new scintillators?
If timing is important for a certain application, then the brightness and the decay time of the scintillator is important. And again, as I earlier said, cerium bromide is a fast scintillator that allows fast timing. Okay. And of the proportional scintillators, this is the best material for fast timing at the moment.
All right. And Matt Alper is asking, what is your general process for examining new high-resolution scintillator materials, or evaluating them for commercial applicability, I suppose?
Well, to evaluate a new scintillation material, we're looking at light output, of course, compared to reference standards. We're looking at resolutions, some more parameters like density, decay time, and so on. And of course, as I said, there are many new materials developed these days, and many of them don't make it to commercial applications because, first of all, they should be growable up to a seizable size. If we publish data on a crystal that can only be made 2 by 2 by 2 millimeter, the applications are a little limited. And further on, it's a question of the market. If there's a certain demand for a material, there's a certain possibility to commercially further exploit it and produce it.
All right, excellent. And Stefania did ask if we'll be having other presentations. As Mark Slattery just mentioned, we are making basically a series on nuclear scintillation. The other presentations we've given so far can be found on BNC YouTube. As for this presentation, this will be it for the Q&A segment. I want to thank everybody again for going ahead and attending, and we're going to be slowly wrapping it up here. And of course, always feel free to contact either Scionix or BNC if you have any questions about potential scintillator applications, or if you have questions or requests for data in lieu of this webinar. All right, thank you.